So we'll get started. In the previous lecture, we were talking about the linearity of what the linearity property of linear systems looks like. So today, I think we're going to talk about various different properties of systems. Okay, we are talking about properties of input-output system. The discussion is from section 2.4.1 of the book. And let me remind you about the specific expressions, because I think it's important to keep those expressions in mind. So we had x dot t equals to at xt plus bt ut, yt equals to ct xt plus dt ut. So right now we are talking about these time varying LTV, linear time varying systems. But when we talk about properties, I'll explain what linearity means in this particular setting. So I can define y as a function of u. So t is the operator. It would be called an input-output operator. So this is the input, this is the output. Input signal, output signal. T is the linear operator. T is the operator. So let me just write t in the form of an operator. Rm to C Rp. So one important note here, I'm not writing u as a function of t and y as a function of t here, even though y is a function of t and u is a function of t here. And that's because I'm viewing u as a function, as a continuous function from R to Rm, and I'm viewing y as a continuous function from R to Rp. As you might have seen, some things that we discussed, when you are thinking about a system, sometimes we have only the input-output description of the system, which is this, and sometimes we also know about the state dynamics of that system. Many a times, systems that we are engineering, we will know what the state dynamics would be, or we can at least figure out what the state dynamics would be. If it's a physical process, or a biological process, or a chemical process, we will probably only have the input-output characteristics, and even the output can only be measured if you have a sensor. If you don't have a sensor, there's no way to measure the output y. So an example of that is, for instance, cancer. So you know the radiation and you know what the tumor size after the radiation is going to look like, but how exactly that radiation is killing the cancerous cells and what's happening over long periods of time, which is the internal state description of the system, of a biological system, that part is still unknown. To some extent it's unknown, to some extent it's known. But if you ask me, for tumor growth, do we know the input or do we know the state equation? We don't. All we know is if you send the radiation in, the cells are going to stop growing, or the cancerous cells are going to die. That's the only characteristics we have certainty over. So we understand the input-output characteristic, we don't understand the state dynamics of those systems. And naturally, as science progresses, as people do research, they tend to have a better and better understanding of what that x dot t equation looks like. So whenever something is written in this form, it's the state space equation. We have the state update function and we have the observation function. Whenever we write things in this particular fashion, then it means that we know the input output characteristics, but we probably do not have the state of the I mean, we don't understand what the state transition function looks like, because it's hidden. It's something that's encapsulated. It's something that we did not create, humans did not create. So therefore, it's very difficult to model that, identify what the state dynamics of that system is going to look like. Okay, so there are desirable properties of these input-output systems. Y equals to Tu. So we are going to talk about 4 properties here: linearity, memoryless versus with memory, causality, and fourth, time invariance. The linearity aspect of things is something we discussed in the previous class. So what does linearity say? I have y1 equals to tu1, y2 equals to tu2, alpha 1 in R, alpha 2 in R. System is linear if and only if T alpha 1 u1 plus alpha 2 u2 Okay, so a system is linear if you take a linear combination of input, the output is actually the linear combination of the outputs. So this is y1, this is y2. So if you have a system and you observe this pattern in the input output behavior of the system, then it means that the system is a linear system. To give you an example, let's look at this particular let's look at the solution to this system. This is yt is equal to ct. This is something we did in the previous class. So we talked about this particular expression in the previous lecture. So if I assume my x naught is equals to 0, then it's a linear system. Generally speaking, throughout this class as well as in systems theory, we typically assume that the initial state is equal to 0, x naught equals to 0. Anyone knows why we assume that the x naught is equal to 0? My body temperature is 98.4 degrees Fahrenheit. It's not 0. And thankfully, it's not 0, which would mean that I'm dead, right? So,
is it normalized? Like you take the nominal conditions and normalize them and then start.
I don't think I would call that normalize. Normalize has something to do with division. We're not really dividing something, but we are looking at perturbations around the equilibrium point. Okay. So typically the initial condition is equal to 0 because you have like some nominal initial condition and you're just looking at perturbations around that initial condition. And so you assume that the initial perturbation is 0, the system runs for a certain amount of time, and then you want to figure out under the specific control action how much the perturbation is of the updated system. Okay. So that's why we assume that x naught is equal to 0. So if you are starting with this particular expression and your x naught is equal to 0, then your system is a linear system. What happens when x naught is not equal to 0? Then you have this particular non-trivial thing that gets added to this yt, which is the term due to the initial condition, and that creates a problem with this particular definition. So you don't have alpha 1 TUN plus alpha 2 TU2. You don't get that thing. You have this additional term that gets added because of this particular expression. So that's where the definition breaks down. It still maintains some sort of linearity, but the initial condition is the one that's causing it to behave in a somewhat different manner. So this is the response of the system. This is the observation of the system because of the action. And this is the observation of the system because of the initial condition. So your observation is divided into two parts. One which is due to the action, the other one which is due to the initial condition. And in some cases, this particular term is going to die out very quickly. Okay, so whatever is the initial condition, whatever is the observation part due to the initial condition, that will die out quickly, in which case it'll behave after that particular point of time, it'll almost behave like a linear system. Okay. This thing is known as the principle of superposition. Which is, a lot of these terms are pretty old. So in the newer terminology, we'll call it a linear system. But if you were born in 1800s and you were taking this class in 1820 or something, then they'll call it principle of superposition because you superimpose two actions. The output is the sum of the two actions, sum of the output of the two actions. So that's the superposition principle. And in the modern terminology, we call it a linear system because we are looking at it from an operator theoretic perspective. We are not looking at it from the input output perspective. We are looking at an operator that's mapping the input to the output. Okay, any questions so far on the linearity definition for linear system? Okay. Let's look at the memoryless versus with memory system. The reason why people think about superposition principle is imagine this scenario. I'm sure as a kid you would have done it. I don't know how many of you do it now. So you have a lake or a pond and you throw a pebble in the pond, right? And then there are ripples that comes out because of this when the pebble hits the surface of the water. Then you take another pebble and you throw it in the water. Now the waveforms are superposition of the two waveforms that are formed, right? So that's where the superposition principle came from. And it actually happens a lot in many situations where you have two waveforms, they are interfering with each other, and then the overall waveform that you observe is going to be the sum of the two waveforms. So that's the origin of superposition. Let's look at the second behavior, memoryless. So T is memoryless if Yt is just a function of Ut. Otherwise, you have memory. So taking an example from the book, figure 2.2, you have a current source. You have a resistor. Do you remember what the input output equation looks like? So Vt equals to R times It. So your output is just a function of the current input. It doesn't remember the inputs in the past. Contrast this with something like a capacitor. Anyone remembers what the equation looks like, the input output equation for this? I don't actually, so let me read it up. Okay, now I know. It's 1 over C integral minus infinity to t it dt, I tau d tau. So the output is an integral of the input all the way going to minus infinity to the current time. So this is a system with memory. This is a memoryless system. So what are good examples of, okay, I'll let you guys write. But then I want to think about what are the good examples of memoryless system. So what's a good example of a memoryless system? So typically speaking, any sensor is a memoryless system because you want to measure the instantaneous information. So if I have a thermometer, I want to measure my body temperature. It doesn't have any memory. As soon as I put it on my body, it tells me exactly what the current temperature of the body is. So that's a memoryless system. Naturally, whenever you have a capacitor within a circuit, then it has a memory because the capacitor tends to integrate. It holds charge, so therefore it tends to integrate the current that has been sent through it so far, and that leads to a memory system with memory kind of behavior. I've written some other examples. Amplifiers. So right now I have a mic. And this mic is streaming the information, whatever voice is coming to the mic, it's streaming all that information to the camera. That's a memoryless system. It's memoryless because it's not taking my previous voices, adding it up to the current voice and then sending it to the camera. So that's a memoryless system. So amplifiers are memoryless system. It doesn't have any memory. Whenever you have averaging or whenever you have integration, then you have a memory, and then your system is a function of the memory. Derivatives would be again memoryless because it doesn't depend on the past information. You're taking the current derivative of the, let's say, a current, in which case it becomes a memoryless system, because yt is just a function of ut, and in that case in derivative of ut. Let's talk about causality. So T is causal if yt depends on u tau, tau less than equal to t. So whatever has happened in the past, whatever actions you have taken in the past, all of that influences yt, but yt doesn't depend on the future actions. So yt does not depend on u tau, tau greater than t. So that's a causal system. Okay, so let's try to write it a bit formally. So I have ut, u tau t is given by ut t less than equal to tau and 0 t greater than tau. And then we have y tau equals to tu tau, which is equal to tu tau. Oh, this is also a function of time, so I need to make this, evaluate this at time tau. And this should hold true for all tau in R. Then it's a causal system. So in plain English, yt doesn't depend on the future actions. More formally, in the language of linear operator, this is how you want to write it. Okay. What are examples? So when are things non-causal? So causal systems, I think you all agree, like many things that we do on a day-to-day basis, it's a causal system. My air conditioning system is a causal system. My car is a causal system. Only when I apply an action, that action gets applied. And whatever observations I'm making right now is function of the past observations or past actions that I have applied on that system. What are examples of non-causal systems? So typically non-causal systems happens when you are trying to do some historical data analysis. So some examples are, you have a signal which is pretty sporadic and you want to figure out what happened in between. Okay, so at every point of time you're going to look at the future information, you're going to look at the past information and you're trying to estimate what exactly would have happened. So that's the case of non-causality. So filters are, you could have causal filters, but you could have non-causal filters. So one of the simplest non-causal filter is an averaging, moving window averaging filter. So so you can have a situation where your yt is summation of u tau. Well, I'm doing summation, but maybe I should do integration. 1 over 2, let me put tau, minus tau to tau, us ds. So this is non-causal. Minus tau plus t, tau plus t. Yeah. Another example of a non-causal system is US jobs report. So you can think of a country as an economic system, and the input, anybody knows what the input is? The interest rates, and yeah, interest rates is one of the bigger inputs, and then there is monetary tightening or monetary easing, quantitative easing. So those are sort of the two inputs, two levers that the government has to increase the jobs or reduce the jobs. So YT is essentially the number of jobs created or destroyed in the economy, and UT is essentially two-dimensional, how much money to inject into the economy and what the interest rates of the central bank is going to be. So those are the two, like two-dimensional input, one-dimensional output. And so ideally, you would argue that the government should have all the information about who is getting what jobs at what point of time in near real time. So if I get a job today, the government will probably know today that I got a job, and therefore YT will go up by 1 or go down by 1, depending on what happened. But turns out that the government job reports are not that accurate. They don't get all the information in real time. So generally speaking, they have some understanding of how many jobs were created in January of 2026. But when the March of 2026 comes, they are going to update the estimate of what happened in January 2026 based on the data from February and based on the data from March. Okay, so they start with a causal filter, and then they come up with a non-causal filter in order to update the estimate, and the updated estimate is a better estimate of how many jobs were created or destroyed in a specific month. Okay. Once again, the model of the economy, you can only see the input-output expression. You don't know what the state space of the system looks like. Nobody knows what the state space of US economy is. And how does that state space interact with other states of the US economy? So nobody knows what AT looks like. Nobody knows what BT looks like. All they observe is the government did something and how many jobs were created or destroyed. Those are the only two things. At least from some perspective, those are the two things that the government is very interested in. Okay, any questions so far on causality? So filtering is typically, in signal processing, you will have a lot of non-causal operators, but in controls, you typically only deal with causal operators. Okay. Oh, the fourth one is time invariance. Let me write down the plain English language definition. So if I translate my U, then the output also gets translated accordingly. So if uh, input is ut, then output is yt. If my input is u t minus t naught, then my output is y t minus t naught. That's the plain language definition. Now let's look at it from a mathematical or operator perspective. So you define an operator So T is time invariant. If and only if, well, I'll just write IFF. I guess I'm doing operator overloading here. Let me try to explain what's happening. So here I'm actually doing an operator overloading. So Q alpha here is a map from C R R P to C R R P. But it's the same shift operator. There's no change. Okay, so what am I doing? I'm shifting this input and I'm looking at the output, and hopefully the output is also shifted. If the output is also shifted in an appropriate sense, then you have time invariance, and then it's a time invariant system. Otherwise, it's a time varying system. Now, let me give you an example. I have an air conditioning system at my house. I turned on the air conditioning system at 8 a.m. Let's say every day at morning 8 a.m. I turn on my air conditioning system, and at night 8 p.m. I turn it off. That's my control policy. So UT is equal to 1, 8 a.m. to 8 p.m. UT equals to 0, 8 p.m. to 8 a.m. That's my action. I'm going to change my action. I'm going to translate it. I'm going to shift it by 1 hour. So now my UT is going to be 1 from 7 a.m. to 7 p.m. and it's going to be off, UT equals to 0, from 7 p.m. to 7 a.m. Do you think that the output, which is the temperature of my house, well, okay, perfect. So do you think that if temperature of my house is the output, would that also shift appropriately? Right? So the AC will try to maintain the temperature. Let's say the set point is 72 degrees Fahrenheit. The output, which is the temperature of my house, will remain 72 degrees Fahrenheit between 7 a.m. to 7 p.m. and then it will change to whatever the natural temperature is from 7 p.m. to 7 a.m. Perfect. What about the electricity bill? If that's my observation, that's my output. My output is not the temperature of my house. I don't have a sensor to measure the temperature of my house. But I have a smart meter at my home and I can measure what the electricity bill is going to be. Is that going to satisfy this property, time invariance? Anybody knows? Anybody who has done this measurement? No? So it turns out that it's not time invariant. And the reason is very cool. Uh, the electricity consumed by the compressor of the air conditioning system is a linear function of the outdoor temperature. Okay, it's a linear function of the outdoor temperature. So the electricity consumed at 8 a.m. is going to be much higher than the electricity consumed at 7 a.m. So if you look at, if your output is how much electricity, what's the usage of electricity, then your output will not have the same time shift as the input. So in some sense, it certainly depends on what the output is, but in this particular case, in the case of electricity cost, because it depends on the weather, and weather is time varying, it introduces a time varying nature in the output if my output is weather dependent. If my output is what the temperature of my house is, which is kind of weather invariant because I have an air conditioning system, then the output will not really vary. I mean, it will remain the time invariant. It'll maintain the time invariance properties. So time invariant is really a function of what you consider as input and what you consider as output. Any questions on this? No? Okay. Perfect. So let's look at the next topic is the Dirac delta distribution, which is impulse response of the input output system. So let's assume single input, single output for the time being. So ut is in R, yt is in R. Let's assume that y equals to p times u. P is the operator. For the time being, we'll talk about linear operator, and we'll talk about two different types of linear operators. One is time varying, one is time invariant. So definition. We say that P admits an integral representation if and only if there exists a kernel GP such that P of ut equals to so GP is called the kernel of the integral representation. You know, the notion of kernel is very commonly used across a wide range of fields. Anybody has heard of this term kernel before? In what area? Where did you study kernels before? Huh? Machine learning? Operating systems? Perfect. Okay. So in machine learning, there is a notion of kernel. In operating system, there is a notion of kernel. Here, the notion of kernel is quite different from what you have studied in machine learning and in operating system. So just keep in mind that people call it kernel, but kernel has a lot of different meaning in different fields. So here, the meaning of a kernel is something that goes inside an integral. This notion of kernel actually confused me a lot in my early days of graduate school, because I saw kernel at multiple places and I thought they are referring to the same thing, but actually they were referring to completely different things. So it confused me a lot, and I spent a lot of time reading books as to where this notion of kernel came from. And turns out everybody is using their own definition of kernel, which is fine. It's just I did not know that. Okay. So now the question is, I have a linear system. I want to know what the kernel of the linear system looks like. I can measure the output. I have the input because I've logged that information. So I've measured my output information is logged, my input information is logged. I want to figure out what this kernel, GP, looks like. What would you do in order to measure GP, in order to understand what GP looks like? Any idea? Yes?
Put in a known input that is a quick pulse and see what the output is.
Awesome. Okay, so quick pulse. Perfect. Everybody knows what a quick pulse is. Kind of, sort of. Everybody has a feeling. Everybody has taken 3050 or 3551. So quick pulse is something like this. That's a pulse. Okay, quick pulse. All right. We want to make this notion of pulse very concrete in this particular class. So the goal right now, like I know that this is something that you've covered in 3050 and 3551, and we said, okay, there is this Dirac delta thing and it just works beautifully. I want to actually make it concrete, mathematically concrete, because now we are taking a graduate class, so we need to understand what exactly this Dirac delta function or a pulse is. So let me define a function phi n of x. Why are they using x? Maybe I shouldn't use x. I think the notation in the book has not been carefully chosen. So let me use t. Okay, let me just use t for now. So 1 minus, the book is using x, but we are already using x for the state, so I don't want to use that. This is n times minus n absolute value of t Let me pick a function. Okay, I'll let you guys write it. So what is this? I've created a function which actually it's a sequence of functions. So it's not a single function, but a sequence of function indexed by n. So what does this function do? At minus 1 over n, it starts rising linearly all the way to n, and then it starts falling linearly until it reaches 1 by n, 1 over n, and then it remains 0 before this place and after this place. I have a function f from R to R, and let's assume for the time being that it is continuous everywhere. And let's consider this integral f of tau phi n of a minus tau d tau minus infinity to infinity. What is this equal to? Can someone simplify this function for me? So I know that phi n is 0 for like pretty much the entire of real line except for minus 1 over n to n. So can I write this as a minus 1 over n, a plus 1 over n, f tau phi n, a minus tau d tau? Does this make sense? This term is only positive between a minus 1 over n to a plus 1 over n. It's 0 otherwise. Okay, so this looks cool. I want to take the limit n goes to infinity. Can someone tell me what's going to happen to this integral? I let n go to infinity. So what is happening here? This term is not dependent on n. This term is going to blow up to infinity. So this term is going to blow up to infinity. So this term is going to go to infinity. But this term is actually going to shrink, right? So a plus 1 over n to a minus 1 over n. So I want to make sense of what this integral is going to look like if I let n go to infinity. So what should I do? I'll just do it here. So let's say n is very large, right? So f tau, what is f tau approximately equal to? So let's see. F tau is approximately equal to f of a, right? So I'll do a quick and dirty math. So f of a. Now I'm integrating from a minus 1 over n to a plus 1 over n, this particular function. That's actually area under this curve. What is the area under this curve? What's the area under a triangle? Half into 2 over n into n, which is equal to 1. So this is 2 over n, this is n, and I have to multiply it by half. So that gives me the area under the triangle. So it turns out that this is approximately equal to fa times 1. So as I let n go to infinity, this sequence is going to converge to f of a. But remember that the function that phi n is limiting to is actually infinity at origin and it's 0 everywhere else. So that's the pulse we are referring to. It's called the Dirac delta distribution. There is another formal way to define this Dirac delta distribution which uses probability theory, but we are not using probability theory here. So I'm just going to give you what that Dirac delta function looks like. How it is defined, actually it's just a definition. It's not an integrable function. It has no meaning in math. Well, it has some meaning in math, but it is essentially meant to probe a function at a specific point. So what we have proved is the following lemma. This is lemma 2.1 in the book. F from R to R is continuous at A in R. Then limit n goes to infinity, integral and so we use this, we denote this particular integral by, this is just the notation convention. And in 3050 and 3551, this is the impulse at t equals to a. So at time t equals to a, you give it an impulse, and it's the same as Dirac delta distribution, it's the same as Dirac delta function, it's the same as impulse at time t equals to a. And this is just the notation. Whenever I write this, I mean this. Okay? Wherever in the book you see this expression, what you actually mean is this particular expression. But writing all that limit and phi n and all of that stuff becomes troubling. So people write it in this particular fashion. There are many ways to construct this impulse function. So what I have used here is a triangle, but you could also use something like this. That's also a valid impulse function. And so I don't know what you have studied before, but it would be either the triangle, limit of this triangle as an impulse function, or this rectangle as an impulse function. Both of them are valid because it leads to the same result. Okay. Now I have a linear system. I have the input, I have the output. I want to figure out what the kernel of that linear system looks like. What should I do? The idea is that let's give it an impulse response and see what the response of the system looks like to an impulse. So what we are interested in is okay. It turns out that P delta is the same as GP. So in the case of LTI system, P delta is equal to integral P delta T what is this equal to? I just have to substitute tau equals to 0 here, and this is my GP of T. For LTV system, I have P let me remind you what LTV system says. PFT equals to integral minus infinity to infinity F tau GP T tau T tau. What happens if I replace F with delta? So what is P delta T? This is minus infinity to infinity delta tau GP T tau D tau. Okay. However, this is time varying, so I can put an impulse at some other time. So I put an impulse at time 0, I get this expression. Let me shift the impulse operation slightly. Let me use Q alpha, and this would be GP T alpha. So this is the shift operator we had talked about earlier, Q alpha. So if I shift the impulse operation, then my GP will be the impulse output. So at time alpha, I give it an impulse and I look at what the output of the system looks like at all points of time t. That gives me this kernel of the function GP. And it turns out that by using the impulse, which is something that you all know because it's something that you have studied in your signals and systems, that if you have an LTI system, so this is what LTI system was, what the subject of study in your signals and systems or feedback control systems class was. And what you had studied there is that a system is characterized by its impulse response, right? That's something you have studied before. And this is the proof of that particular statement, which is the linear system has a kernel, and the way to get to know what the kernel looks like is to give it an impulse response, look at what the response of the system looks like. So this is actually y of t under impulse input at time 0. And this one is impulse input at time alpha. Okay, so that's the impulse response of a system. So the Dirac delta distribution is this function delta, which gives you the information about what the function looks like at a specific point. So you multiply delta alpha minus tau to f tau, you take the integral. What we mean by this particular expression is we are taking the limit of this particular integral, and it should be equal to fa as long as f is continuous at a. For most part of this lecture, we will assume that the control action is continuous function, but as we have seen, you can have a piecewise continuous control function. So you can be a piecewise continuous function, and that's also completely fine. You have all the solutions and everything for those kind of systems as well. So anyways, in this particular case, we are using this function which is continuous at a. When we use the Dirac delta function, what we mean by that is a limiting behavior of this sort of a function where the integral is very well defined. And then if we want to characterize a LTI system, if we want to know what this LTI system, how this system is going to perform, well, the system is going to perform according to a kernel. Then the question becomes, how do I know what the kernel of the system looks like? Well, you give it an impulse as an input, you look at the response of the system, that will give you the kernel of the system. For the LTV system, what do? Well, you can do the same thing, but because it's time varying, you have to give it an impulse at time alpha, and then you have to look at the response of the system at time t, and you store that particular information in the kernel GP. That gives you the kernel for the time varying system. Now we want to extend this idea to multi-input, multi-output system, and the idea is not too different. All the stuff that we talked about will work even for the multi-input, multi-output system. And let me give you the expression for that. So now my y U So HP is a function from R cross R to RP cross M. This is section 2.4.4. So this is same as saying YIT equals to minus infinity to infinity Okay. So for LTI system, you can give it an impulse input. You can look at the output that gives you the kernel of the system. What happens when you have multi-input, multi-output linear system? In that case, the kernel function will no longer be a real valued function. It'll actually be a matrix valued function. So this is a matrix valued function. You multiply this matrix by another matrix, which is Rm. So U tau is an Rm. This one is an Rp cross M. You multiply the P cross M matrix by an M dimensional vector. What you get is a P dimensional vector as an output. So we are integrating all of this. We get a P dimensional vector as an in the output. Just a small note. This P is the same as this P, and this P is small p, which is the dimension of the measurement space. Now the question again becomes, how do you know what the output of the system is going to look like? How do you characterize this particular matrix? Well, the way to characterize this matrix is again to give it an impulse input at specific time, and then you can look at the output, and that will give you the expression for each element of this matrix. So HP of T tau, just to give you a feel for it, what this value is going to look like. This is something that we will study in the next class, but I want to show you what it's going to look like, because then it becomes much more concrete. So it might look something like this. So this HP matrix could look something like this. It could have a more complicated expressions as well. But this is what every element of this particular matrix is a function of time. I'm actually using t minus tau because I'm using the time invariant representation here. I'm assuming that the system is LTI. If the system was not LTI, this could be for the LTI case. You could have something like this, which is for a LTV system, linear time varying system. So you have a matrix. Every element of that matrix is a function of time, both time t. Sorry, this should be t comma tau. So in this particular matrix, t minus tau appears together everywhere. So that leads to an LTI kind of behavior, linear time invariant behavior. Whereas in this case, because you don't have t minus tau everywhere, you have a time varying LTV type of behavior in this particular system. Okay, so this is what it's going to look like. And how do you find this matrix? Well, you apply this particular approach. So you set all the other controls to be equal to 0. You put an impulse response to a specific, so uj is equal to the impulse input, and you look at the output is actually going to be this HP, the element of that HP matrix, HPIJ matrix. One important note here, so this holds for general linear systems. One important note is, if the system is causal, then there is certain further structure in this kernel function. And the reason why there is a structure in the kernel function is because it's non-anticipative, in the sense that the future u's are not needed to compute y of t. So what sort of structure will we have in the causal system? For all t less than tau, HP of t tau is going to be equal to 0. This is the 0 matrix. So I know I have written it as a scalar, but what I actually mean is a 0 matrix of appropriate dimension. Okay. So that gives us some idea of looking at the input-output behavior of the system, understanding how to characterize that system, whether it's a linear system, non-linear system, whether it's a causal system, non-causal system. Just by looking at the input-output characteristics, you should be able to figure that out. Now the question becomes, how do we measure what the input-output characteristic is going to look like? Like, how do we get that information? Well, the way to get that information is through the impulse response of the system. You give it an impulse input, you look at what's happening at the output level, and that will give you the information, a lot of information about the system. If it is an LTI system, the impulse response characterizes the entire system at once. If it is an LTV system, then you have to do impulse at every point of time, and that becomes a challenging affair. So to give you an example, you have an LTI system, you give it an impulse right now, you collect the data for the system, you are done. You're done forever. You have an LTV system, you collect the data now, you just have the kernel information for the current tau, and then you have to do it 1 minute later, and then you will get it for the next tau, and then you do it 1 minute later, and then you get it for the next tau, and so on and so forth. So for time varying system, it's a bit complicated to get the impulse response because you have to do that experiments multiple number of times in order to get that information. Have you ever had a medicine and the doctor said have it before the meal or have it after the meal or have it at night or have it in the morning? Why is that? Because our body is an LTV system. Our body is not an LTI system. So at night we are sleeping. So before sleeping, we are supposed to take a certain class of medicine. When we are awake, our body is moving around. And at that point of time, you're supposed to take some other classes of drugs or other classes of inputs. And that's because we are an LTV system. And so, how do the doctors know at what point of time this drug should be administered? Well, during the clinical trials, they do all these experiments. So, they give you the medicine before the meal, they give you the medicine after the meal, they give you the medicine at night, they give you the medicine in the morning. Not you, but different types of patients. And that's how they collect the data as to what the response of the body is going to look like. And what the current problem is in medical sciences is the input output characteristics of every person is very different from other I mean, not very, but slightly different from other people. And so there is this whole new area of personalized drug. I don't know how many of you have heard of that, personalized drug. So they want to figure out what your LTV system looks like, and then they'll design the drug concoction for your LTV system. Okay, so that's the cutting edge research in the medical sciences industry. So just something to keep in mind, it's not like LTV systems are useless. It's just that dealing with an LTV system is a bit more complicated. And so you get paid a lot more money if you're dealing with LTV system than if you're dealing with LTI system. So that's why doctors get paid more than what we get paid. Anyways. So that's pretty much all I have for today's class. Any questions so far? No? Okay. Wonderful. So in the next class, we'll go a little deeper into the linear algebra. We are done with chapter 2 of the book, and we are going to start talking about chapter 3 in the next class, which is response of continuous time system. So I'm going to be doing a review of, not a review, but we are going to talk about Jordan canonical form. How many of you have heard of this term, Jordan canonical form? A few of you, okay. So we'll talk about similarity transformation, Jordan canonical form, matrix exponential. So a bulk of the next few lectures is going to be a lot of linear algebra, a lot of eigenvalues, and a lot of eigenvectors. So please brush up on eigenvalues and eigenvectors before you come to the next class. Thank you so much, and see you on Thursday.